Okay, hello everyone, my name is David and I'm going to talk about interactive tests and interactive documentation. The presentation itself will contain some interactive examples, so if you want to follow along, you can try it out on your own. You can go to the first URL here, and the second link, you can actually run some PureScript compiler in your browser on your own and try out some of these examples and modify the code without installing anything. So the talk has two parts. The first part I will talk about PureScript library called Flare. It's somehow extending the notion of a signal to something that incorporates also input elements. And then the second part is the main part, where I will extend that to create user interfaces in an automatic way based on type level information. So first part, extending signals to what I call flares. So here's a little example of what we can do with this library. Code will be in PureScript. If you know Haskell, shouldn't be any problem to read it. If you don't know either of the languages, please feel free to ask me. But I hope you can still take away something. So with this 2 lines of code here, basically defining, we can define this short little user interface here. That's kind of reactive, so we can change values here and the result will just immediately be shown below. And we define these 2 input fields with these 2 commands. So int creates an input field for a number. It has a label that's shown down below and a default value that will be present at the beginning. And if you're familiar with these 2 operators, it says that we fmap or map the power function over the first input field and then apply the whole thing to the second input field. And I'm going to explain that in a bit more detail. This idea of creating user interfaces in this applicative style is not my own idea. There's a related Haskell library, and you can find it here. The implementation is completely different though, and using PureScript we can do it on the web and create reactive user web interfaces. So starting points are signals. If you've never heard of signals, you can think of them as, at least conceptually, as being functions from some notion of time to an output type A. So signals over A is time-dependent function that gives you an A at every point in time. So for example, you can see that the mouse position is just a signal of a tuple int, int, and it's shown here and updates as I move the cursor. Seconds you can think of as a signal of ints that shows the number of seconds since I opened up the browser, opened up this document. And if I press the A key, then false turns to true. So key press is a function that takes a key and returns a signal of bools. Signals are functors, which means that you can build up more complex applications by using a pure function such as drawClock, which takes an int and returns a simple drawing of a clock. And then I can just use this seconds signal, map the function drawClock over this signal of integers, and I will get back a signal of drawings. So it's a time-dependent drawing, which I can just render on screen, and you get this small animation. Signals are also applicatives, which means we can do the same thing for multiple parameters. So here I'm using two signals, the x coordinate of the mouse position and the width of the window. With this applicative style, I can apply the divide function to both of these signals, and I will get back a signal of number, which just represents the ratio of the x coordinate divided by the window width. Then I can f-map that ratio over this progress bar function, which draws this bar down here, and you can see that it updates to the current position of my mouse. If I would change the window width, it would also immediately react to that. But now we want to somehow add input elements to that. And the question is, how can we render those input elements on the screen if we just have an expression like this? So you can think of int base 2 being a signal that gives me back the current value in the input field. But I also need to know what to render on the screen, what kind of input elements I have to show on the screen if I just want to write code like this. And we can do that by extending the signals to flares. So in order to explain how flare is implemented, I will take a short interlude about something a little bit more abstract. So if you have a base functor f over some type b, you could annotate it with a new type a and still write a functor instance for that. So this data type n, or which stands for annotated, is basically just the base functor fb, so functor f over some type b, but in addition it has a value of type a. It's easy to write a functor instance because we can just ignore this annotation. We just leave the a alone and use map from the base functor. So in PureScript, fmap is called simply map. Then we can ask, are these annotated functors also applicative functors? Well, we can just try to write an instance for applicative. We have to implement pure and apply. But then we see that we have a problem. We can reuse pure and apply from the base functor, but we somehow have to create a value of type A here out of nothing. And we have to combine two values of type A to a new value of type A. And that could remind you of the structure of a monoid, where we can create values out of nothing, and we can combine two values to create a new value of type A. So if we add a constraint that this annotation type is a monoid, we can use the empty or the identity value for pure, and we can use the semigroup append or monoidal append operation in apply. So this compiles, but we are not completely done because we also have to check if all the applicative laws hold. But somehow I think it looks so symmetric that so when I saw this the first time, I thought, well, it has to somehow fulfill the laws. It looks right somehow. And you can also go through the proofs. I don't want to show it in detail. I just want to mention that you really need the identity law and the associativity law of monoid in order to prove the applicative laws. So finally, a flare, what is really just a flare over some type A is really just a signal over the same output type A, but it's annotated with a list of HTML elements that I want to render on the screen. And list of anything is a monoid, with the empty list being the identity element and list concatenation being the append operation. So just writing this and having an instance for applicative for this annotated functors, flares will also be applicatives. And then we can define some basic elements like a text input, number input, or checkbox. They're simply called string, int, or boolean. They take a label, which is just a string, the thing on the left-hand side. They take a default value and return a flare of a specific type. And then you can write simple user interfaces in a very concise way by just using map and apply, and you get something like this. So this is really the full code that creates this little user interface. What I really like about this is that I can easily create both interactive and animated plots, for example. So here I have a function that I don't show. It takes a number of parameters and it plots a shape like this on the left-hand side. And I can easily turn this into an interactive, no, it doesn't work. Interactive animation by just defining a few flare components that take the right ranges. And then I can play around with different shapes. I can even have a color input, change that. And I can still use the underlying signal. So AnimationFrame, for example, is a signal that on every redraw of the browser yields the current time, and I can use that to dynamically change that plot, for example. So it's just a pure function plot, but then turned into an interactive animation by by a few lines of code. So the second part will be about a library called FlareCheck. And the idea is the following. Right now what we had to do was we have a function that takes two integers, returns an integer, but we still had to write int and int here in order to actually run it. But somehow we're in a strongly typed language. We could use the type system information to create the right input elements for us. So what I want to do is to turn the upper part here into just this. Just want to call FlareCheck the power function, and it should create the right user interface. And that reminded me of QuickCheck, because you can do similar things there. So let me remind you just quickly what the essence of QuickCheck is. It defines two type classes. One is called arbitrary, and it provides a way to create arbitrary values of some type. So out of nothing, it creates a value of type A. And the second type class is called testable, and it turns a value of type T into some kind of result that QuickCheck can work with. So if that result would somehow signal that the test failed, QuickCheck would show that on the console, for example. And the thing that makes QuickCheck really powerful is this instance, which says that if A is arbitrary and T is testable, then a function from A to T is also testable. Which means we can, the QuickCheck function itself takes an argument that has to be testable. But now we can run QuickCheck on functions that take an A, because QuickCheck can just call arbitrary to generate random input values and then test the result. And it's also powerful because it's somehow recursive. If you plug in A to T for T, you immediately get a whole succession of different instances for functions of multiple parameters. And we can do something similar with flares. So in lack of a better name, my type class is called flammable. It provides a function called spark, and it somehow creates a value of type A out of nothing by providing a user input element where I can input values of type A. And the other type class is called interactive. It provides a way to turn a flare of type T into something that I can render on the screen. Again, it has this instance that if an input type A is flammable and the output type T is interactive, then a function from A to T is also interactive, and it's recursive in the same way. Then I can go ahead and write a lot of instances for that. For Boolean, for example, it would be just a checkbox. For string, it would be a text element, and so on. And I can write instances for interactive. There's lots more even. And then I can do things like this. I can just call FlareCheck length. Length is a function that takes a string and returns an int. And it gives me this user interface. I can type some text, and we'll just immediately update the value. It's not so easy to see here, but it also does some syntax highlighting on the output. So a few more examples. We can also do multiple parameters. We just call FlareCheck on a given function. It takes an int and a string, returns a maybe int. And now FlareCheck will just create two input elements, one for numbers. You can see that it's different. It has small buttons to update the number, and then one for a string input. And again, the output, it knows how to render a maybe value on the screen by, again, giving us some kind of syntax highlighting, and provide some visual feedback if it returns nothing. And of course, we can also call this on more complicated constructs. So we could call FlareCheck filter even. Well, the type checker knows that filter even has type array int to array int. It takes a list of integers and just returns all the even integers. And then FlareCheck will provide a way to input a list of integers by just giving me a text input where I can add comma-separated values, and I can put some values in, and it would just show me the even numbers. So you might think, okay, this is maybe nice, but well, is it really useful in some sense? Because I could also just open up REPL and test my functions there. That's certainly true for simple functions like that. There's one more example with booleans, which I forgot. So will give me some checkboxes. But there's like two reasons for why I think this is still useful. First of all, we sometimes have output values which cannot be printed on a REPL in the console. For example, if you output a drawing, or I wrote some module which works on color values, it's much nicer to show them in the browser than in the REPL. And it's also nice to create interactive documentations. So this is an example of module documentation for PureScript module called data array. And this whole document is basically automatically generated from the source code of data array with a few explicit type annotations that I need, because we have some polymorphic functions and I need to provide some concrete type to get a valid test. You would have to do the same thing in QuickCheck. But then it prints one of these boxes for each function in the module, shows me the documentation string, and then provides interface where I can test the functions immediately, and I think that's something which can be useful sometimes because not everything can be inferred from the type, and sometimes not everything can be inferred from the documentation string. Finally, I wanted to say thanks to the organizers of LambdaConf, a very nice conference, to all PureScript developers who helped me with these two libraries, to Gabriel Gonzalez for the idea for the Flare library, Bodil Stokke for PureScript Signal, and Phil Freeman to help me with the instance in FlareCheck. And finally, thanks to you for listening.